Hey guys, welcome back to another RASK Maths video. And in this video I'm going to be showing you guys how we can convert linear recurrences, such as the one you see here, into a deductive series, which basically just means we have a of n in terms of some function of just n. So not using any of the previous, immediately previous terms, but rather just using n on its own. And the way we're going to do this is using generating functions. So it's not exactly generating functions, but we're going to be making use of a function which has this as its coefficient so that we can then find an alternate representation of it and then easily work out another way to represent its coefficients. So I'll show you guys what I mean, but before we get started, let's just list out a few terms of this series. So let me make a table with n and a of n. And I guess we'll go up to the fourth term because after that they get quite large. So we know a of 0 is 2 and a of 1 is already 7. And then we can work out what a of 2 is because that's going to be 7 times 7 minus 10 times 2, which is 29. A of 3 is going to be 7 times 29 minus 10 times 7, which is, let's see if I can do this. So that's going to be 203 minus 70, or 133. And then the fourth term is going to be 7 times 133 minus 290. Just do that quickly. So we get 931 minus 10 times 29, which is just going to be 641, I believe. Okay, so now you can see we have a few values of n, and you can see there's not really a pattern we can spot immediately, which gives us the next term. So it's going to be quite difficult for us to get a representation of a of n in terms of just f of n. So this next step might seem a bit weird, but trust me, what we're going to do is we're going to make a function called f of x, and let me do this in green. So let's make a function of f of x, which basically has a of x as its coefficients. So f of x is going to have a of 0 of x to the 0 plus a1 x to the 1 plus a2 x to the 2 going on. You can see why this is called a generating function, similar to that because you'll be using the x's to separate out the coefficients. So in our particular example here for this recurrence relationship, this is going to give us 2x to 0, which is just 2, plus 7x plus 29x squared plus 133x to the 3 plus 641x to the 4, continuing. And yeah, we're going to define this function to just have the coefficients as the terms of a of n. And let me show you why we do this. So one thing you'll notice is because the next terms of a of n is defined as 7 times the previous term minus 10 times the term before that, what if there was something we could do, something we could add to this function, which could effectively cancel out a bunch of terms, leaving us with just a few polynomials, and that would give us a new representation. So I'm going to go over the details, but essentially if you take f of x, think about this, and then we want to subtract 7 times all the previous values. So let's subtract 7 times f of x. And wait, not just subtract 7, because we also want to multiply everything, want to move everything up to affect the next term. So if we subtract 7 multiplied by f of x, hopefully you can see what's going to happen here. If we multiply everything by 7, I'm just going to write terms underneath. We're going to get minus 14x minus 49x squared minus 7 times 129, which was 203 x cubed. And this is going to go on. So that's the first part. We're taking away the 7 and 7 of the previous term. And now what we're also going to do is see how we minus 10 times the 2 previous terms. So I'm going to add 10 times x squared times f of x. this x squared effectively just moves all terms up, so they now affect the term 2 terms after, which means these all going to cancel out with the original a of n's they create. Hopefully that makes sense, and I'll show you guys what happens when we add in these minus 10 terms. So sorry, when we add in this plus 10 x squared term. So now this 20 becomes plus 20 x squared. This becomes plus 70 x cubed. 29x squared becomes plus 290x to the 4, and that continues. So what can you see here? Well, this diagonal here, this is the original term. This is cancelling out that plus 7 with minus 7 multiplied by the previous term brought over. And same thing here, this is taking the term 2 previous across and adding 10 times it, using x to denote the actual term to affect. So essentially, we're multiplying it by 10, cancel out that 10 there, and then we also add the x squared so that it now affects the term 2 times in front, which is how this recurrence relationship is defined. And what that ultimately results in is this diagonal, 7 and the 10 together, they cancel out this plus 7 and minus 10. So this whole diagonal is going to get cancelled out. You can see it's plus 20, plus 29, so that's plus 49 minus 49. This, and then it cancels out all diagonals because these are both infinite series. This diagonal also gets cancelled out. This one would also get cancelled out, except I haven't written this term in. So all in all, you can see that we've managed to cancel out, I'm going to use purple, we can cancel out all of these diagonals of 3 on and on, which leaves us with just these 3 terms at the front remaining. Okay, so what does this tell us? Well, that means that once we've all cancelled everything out, f of x minus 7x f of x plus 10x squared f of x is just equal to 2 plus 7x minus 14x. So let me write this a bit neater. This means f of x minus 7x f of x plus 10x squared f of x is equal to 2 minus 7x. With all these cancellations and strategically picking these minus 7 and plus 10 to cancel out the 2, which is how you construct the next term, we're able to cancel out all terms except for the first few. And now using this, we can factor out the f of x to just give us 1 minus 7x plus 10x squared equals 2 minus 7x. And this is going to give us another representation of f of x. So we get 2 minus 7x over, if we just factor this, this is going to give us 1 minus 2x and 1 minus 5x. And on this now, we can just do simple partial fraction decomposition. So I'm going to use the look and cover method. Essentially, hide the one which you want, like this. Let me actually just write out so you understand what's going on. So splitting this into partial fractions, we're going to get this. Now we can just take this over to here, and this is just going to expand as a 1 minus 5x plus b 1 minus 2x is identical to 2 minus 7x. Can choose different values of x. So let's say x is 0.2. That's going to completely cancel out the a term, which gives us 1 minus, so 0.6b is equal to 2 minus 1.4, or b is equal to 5 over 3 times 3 over 5. So therefore b is 1. And now let's take x equals minus, let's say x is 1/2, so that this b term gets cancelled out. And we get a minus a times 1 minus 5 over 2, which is minus 3 over 2, is equal to 2 minus 7 over 2, which is minus 3 over 2. So therefore a is equal to 1. So after completing this partial fraction decomposition, we'll get our nice representation of f of x as simply 1 over 1 minus 2x plus 1 over 1 minus 5x. So remember what f of x actually is. This is a infinite polynomial with coefficients being the actual terms of a series. So if we can figure out a way to now expand this out so that we can get the terms of a series as a different representation, we might be able to figure out another way of representing the terms in terms of just n rather than the recurrence relationship over here. So how can we expand these into their own terms? Well, there's actually multiple ways. And first way is thinking about it like a binomial distribution. So if we use the binomial theorem on this, then we're just going to get an infinite polynomial. So we're going to start with 1 plus minus 1 minus 2x plus minus 1 minus 2 over 2 factorial minus 2x squared, and that's going to carry on. Hopefully you can see here the two negatives cancel out, here two negatives cancel out, and there's also a square. If we add the next term, it would be minus 1 minus 2 minus 3 over 3 factorial with minus 2x to the third. And you can see this thing is essentially just negative 3 factorial, so the factorials will cancel out and the magnitude becomes 1. And then whenever it's an odd power, it's going to have an odd number of negative signs, so all the negative signs cancel out. So ultimately, this gives us just 1 plus 2x plus the magnitude is determined entirely by this, 2 squared x squared plus 2 cubed x cubed, on and on. So that's the first way of thinking about it, and then that's only for this 1 minus 2x. We also have to do the same thing for 1 minus 5x. But there is an easier way of thinking about it, and it's to do with the sum of a geometric sequence. So remember, the sum to infinity of a geometric sequence is 1 minus a over 1 minus r, where r is common ratio and a is the first term. So here what this is saying is a is equal to 1 and r is equal to 2x. And for this infinite sum, they're saying they're saying a is 1 and r is 5x. So now we can start off the first expansion with 1. Next term is going to be 2x. Next term is 4x squared. Next term is 8x cubed, on and on. And same thing here, but with 5x as a common ratio. On and on. Like so. So now what we've done here, and it probably would have been better to write these in terms of what they're actually showing. So this is 1 plus 2 to the 1, x to the 1 plus 2 to the 2, x to the 2, 2 to the 3, x to the 3. And this is 1 plus 5 to the 1, x to the 1, plus 5 to the 2, x to the 2, plus 5 to the 3, x to the 3. Remember the common ratio. So all in all, when we collect like terms, this is going to give us, I'm just going to leave the first term as 2, it doesn't really matter. But hopefully you can see the pattern it's forming now. And this will continue on forever. So you can see the coefficients of each term represent the values in the series. And hopefully it's clear now that a of n can just be written as 2 to the n plus 5 to the n. Like that. And I think that's really cool. We can find a simple deductive sequence by just using a generation function, using some clever cancellations, and then writing it in terms of an infinite series with different summation. And it just pops out just like that. We're able to prove that a of n is 2 to the n plus 5 to the n. So there's our answer. A of n is equal to 2 to the n plus 5 to the n. And we can actually verify this for the first few terms. So obviously it works for the first 3. And then for the fourth term, it's going to be 625 plus 16, which is 641. So thanks for watching. And that was how you can convert a linear recurrence relationship into a deductive sequence. Obviously, you could do this for a general case, and you could also do this for multiple terms. Like, it doesn't have to be 2 or just 1. It can be as many as you want, but you have to think of a more You just have to cancel out more terms and get a more complex complex rational function, which you have to split into partial fractions. So yeah, thanks for watching, and I'll see you guys in a future tutorial. Bye.